Let me see if that actually worked. It looks like I am recording pending, and now I am recording. Good. So with that, and with 53 people in the call and still growing, I would like to introduce today's speaker, Hugo Andrade. Hugo and I have worked together for a number of years now. I started as his examiner. I'm now one of his second advisors for his PhD research. And Hugo has also successfully reached the end of his PhD student career because he is defending his thesis, if I'm not mistaken, in 10 days from now, so March 18th, and he is currently deeply thinking about what life will bring to him after that, and what he would like to do after that. So if any of you want to have a discussion after this meeting with Hugo about his future, don't hesitate to reach out to him. But I think during his research, he has done very interesting work in the process of converting traditionally CPU-centric software to GPU-centric or no, heterogeneous hardware-centric software. And the purpose of today's presentation is that Hugo talks us through some of his learnings and findings and frameworks. So, and with that, I would like to leave the floor to Hugo. And Hugo, please take it away.
All right, Jan, thank you very much for the introduction. Let me see if I can share the screen again without any issues.
Yeah.
So it's still loading for me. Do you see the screen there?
Yeah, but now your slide is suddenly very, very small on my screen. I don't know why that is.
Okay.
Can anyone else confirm that they do? Does the rest of you see a full-fledged?
No, it's very, very small.
No, it's small.
Same
yeah.
here.
Can you try one more time?
Let's try one more time then.
But there is an option always in the Teams that you can zoom in using the scroll button.
Yeah, that's absolutely correct. But the point is that it should come up as full size. So if you go out of presentation mode and then zoom and then try again, Hugo.
Okay, let's see.
You didn't stop sharing, did you? Or you didn't go out of presentation mode?
Is it the same? I just went out of presentation mode.
Okay, then.
Interesting. Can we?
Can you stop sharing? Start that first.
Yes, let's do that.
Now you stop sharing, and now try again. And otherwise, you have to email me the presentation, and I'd be your remote control. Now you're in full screen mode. That's fine. And now you go into presentation mode.
Let's see.
No, same problem. Maybe it's the same problem. Maybe you give the presentation without being in presentation mode.
Exactly. Let's try that. Good. So I'm going to share one more time. I'm sorry about the issue here.
Well, we're now 61 people, so it helps. So no one who just joined missed anything. So let's stay in this mode.
Okay.
So good luck.
Okay.
Take it away.
So let's stay like this. So good afternoon, everyone. Thank you very much, Jan, for the introduction. You actually said most of what I was planning to say in the first slide. My name is Hugo. I'm a PhD candidate in software engineering at Chalmers, and I have a defense coming up on the March 18th. So if the topic is of interest for any of you, and you would like to watch the presentation, you are mostly welcome to do so. I'm also looking for a job for next opportunity. So if you hear or if you know about anything, please contact me and we can further discuss. I am a member of the HolyDev research group, which is headed by Jan Bosch, but my main supervisor is Ivica Crnkovic. I am not sure if he's in the audience or not, but he's also part of the shared projects with Software Center. I'm interested in software processes, software architectures, heterogeneous computing, business analysis, and so forth. I have a wide interest there. The topic of this presentation, which is supporting the migration of software to heterogeneous platforms. And I'm sure that for you that who are not very familiar with the topic, this might sound a bit strange, but I'm sure that along the presentation you will have a pretty good idea of what this is all about. To help understanding, I'm going to start with an example in the automotive domain, which I think is familiar to most of you in the audience. Right now, what we have embedded in cars is something quite modern. We also call them cyberphysical systems. So for instance, if we take a computer vision application using a lot of machine learning, AI, sometimes deep learning, you have what we see there in the picture, trying to identify objects and make decisions on top of that. And there is a series of complications when you develop software for these types of applications, because these systems are inherently distributed. There are very limited resources, so the hardware is limited. It's not possible to expand as we go and as we need more resources for computational power or memory, for instance. And they're also, of course, safety critical, so there are some real-time concerns and safety concerns that need to be kept in mind for these applications. And we see an increasing number of functionalities that are attributed to these types of systems. This increase in functionalities leads to more system performance. We need the performance to be there and available to use in terms of hardware. So in order to do that, we have come to this one of the solutions that we have for that is what we're calling heterogeneous platforms.
Hugo, sorry for interrupting. Can you please use the presentation mode?
Yeah, sorry. Maybe you were not here in the beginning. There is a little bit of a problem that is unknown right now, but I hope it's big enough for you to see the images there.
Okay.
If I go to presentation mode,
okay.
it becomes even smaller. So I apologize for that.
Thanks.
But continuing here, what we saw in the previous slide is what we say a modern type of application using computer vision, but it was not like that a couple of decades ago. You know, traditionally, the software that is embedded in cars were pretty simple in terms of functionalities and in terms of architecture. So you might have these ECUs that are connected via the CAN bus, and they interact with the vehicle mechanics via sensors and actuators. And then you might have one ECU for each type of functionality there. So you have one ECU for braking, one ECU for fuel injection, and so forth. What we see here is an evolution between the traditional type of hardware architecture to a more modern one, in which you have different types of processing units that are available for use. So for instance, you might even have an FPGA that is tightly connected to the ECU module in a car, where part of the computation is already processed on the spot before being transferred to a node that is more powerful, maybe doing some inference in some AI models. And then, of course, some of these results are sent to the cloud. So what we see here from the traditional to the modern type of architecture is that there is quite an increase in complexity. So the functionalities are becoming more complex and the architecture is becoming more complex. And we have to handle this in a smart way. If you look at the figure from on the right-hand side, you see that there are different types of processing units. It's not only CPU. So you might have, for instance, a combination of CPU and GPU in the master node in the car, and you might have different FPGAs already in the modules for doing this pre-processing that I just mentioned. But what are the implications of using such different types of processors? Well, the main advantage of using such processors is of course performance, and not only faster execution time, but we also talk about spending less energy, so consuming less energy in the car. And of course, in this domain, this is very important. When it comes to developing software for such platforms, it becomes also challenging, because in the CPU, you have actually soldered and very hard-coded instructions that are pre-selected and pre-made that you have to work with. So, and you might have 4, 8, or 16 cores in the CPU, while on the GPU you might have hundreds of cores to work with. And it's even more challenging in the case of FPGAs, because then you can have thousands of cores. And in the case of FPGAs, you're actually flexible to come up with the instructions that are needed and mostly used in your particular scenario. So it becomes quite challenging for the software developer to come up with a solution that is executable in such platform. The next slide is just one example here, just so you see the complexity or the differences in the code level. So, for instance, if you have this very small function here of adding elements of 2 arrays, you might initialize these 2 arrays, as you see on the left. You populate them with some numbers, and then you add the numbers together. So it's pretty straightforward in the C++ example. However, if you want to translate that or migrate that solution to something that is executable and takes advantage of an accelerator like a GPU, then all of a sudden you have to explicitly manage your memory usages there. So you have to go ahead and declare the global aspect of the function. There might be some privacy issues there, and you have to very explicitly tell the function to wait until the GPU finishes the processing, so it goes back to the normal flow of the application. And there's all sorts of problems in terms of that and complexities that is nowadays in the hands of the software developer. For this example in particular, if you have 1 million elements, as you see in the example, you have to calculate the number of blocks that are necessary for this computation to be executed on a GPU, because instead of having a distributed types of thread processing, you have the particular block size that is needed, and then you see from the computation that is needed how many blocks are needed. So this nowadays becomes complex if you're the developer. So this is just one example of complexity at code level. And I got interested into this problem, and of course the natural 2 questions that I had as a PhD candidate was, okay, so what are the main concerns and approaches that are discussed in academia nowadays? Because I know about all these difficulties, but what is it in terms of research? If we go out in academia, what types of problems and what types of solutions will I find? And then, of course, after that, we would go to industry and ask the similar questions. And we will say, what are the challenges in industry regarding software engineering for heterogeneous platforms? So I want to start with the first one. And the first one is we had a systematic literature review to find papers that are relevant to this question. And we had the purpose of identifying the main concerns and approaches in the area that are addressed by scientific literature. So I actually went through the different databases that exist in the search for papers, and we started with 3,000 papers, came up with some criteria to select the papers that are relevant to the purpose of the research. And we found out that a number of concerns were discussed. So, for instance, if you see there in the figure, it's in the form of a mind map. You see they could be categorized into these scheduling, software quality, software architecture, that it might be a bit difficult for you to see due to the size of the the screen there, but I'm going to zoom in, for instance, in the most common aspect that is discussed in the papers, which is scheduling. So there are discussions about load balancing. How do you go about finding the best balance between the processors, because they are available and you have a certain load that needs to be distributed? How do you go about scheduling the whole application, or if you have parts of the applications which are called kernels, or if you have single tasks that need to be distributed? So how do you go about doing that? And of course, there's a concern about utilizing the resources that are there, because if they're there, you want to make sure that you use them. Then you go about software quality, and of course, there's concerns about performance, portability, efficiency, but still you're talking about very technical and low-level aspects like memory management, like maintaining reliability. How do you go about communication between the different distributed processors? How do you go about unifying the memory and so forth? We've also found some aspects related to the software architecture. How do you efficiently distribute the data and you manage the memory? And how do you deal with the constraints that are real time and so forth? So in summary, what we saw there in terms of concerns is that the aspects that are being addressed in academia are quite low level, and they are addressing very specific technological concerns. And it was the same in terms of approaches. We asked for approaches. What are the solutions to these problems that we just identified still in academia? And then we would still look for, load balancing techniques, profiling, master-slave task behavior, scheduling algorithms, and then we would see measurements and evaluations in the papers, which one is best for which situation. How do you go about creating your own scheduler for the tasks, or how do you prepare the task to be queued up and executed? So these are these sorts of things in the level of the research that we found in the papers. But then we were like, okay, we know what's being talked about in the papers, but what is it in industry? What is the reality in industry? Is it the same thing? Are we facing the same problems when we go into industrial contexts? So we did some exploratory case studies with interviews and workshops, and we had the purpose of identifying the challenges in industry. And then we created a similar kind of mind map where we asked for a variety of types of information. So for instance, what type of hardware are you using? Why exactly are you using heterogeneous platform? Is it for performance? Is it for memory? Is it for, what is it? Energy efficiency? What is the purpose of running on the accelerators? And of course, what are the challenges? And in summary, what we found from the interaction with the practitioners in industry is that there are existing functionalities that can use increasing performance. So existing systems, they can always use some type of performance exactly due to the increase in the functionality and the responsibility that is attributed to software nowadays, especially if you go for domains like AI, machine learning, deep learning, using inference and training of models, for instance. We also found out that heterogeneous platforms are desired, but they're not mastered yet, because finding expertise is not easy. And I can speak for myself. For instance, during my education, of course, I heard about GPUs, FPGAs, DSPs, and so forth, but we did not have specific training to develop software for those. So if you go out in the market, it's still kind of a specialized knowledge that we are looking to develop in the market. And of course, handling the complexity that is connected to some of the issues that I talked about, not only in code, but also when it comes to software architecture. You have the different artifacts, you have portions of code, you might have components, and you have to make a decision. What is the data flow going to look like? How is the communication between the different processing units are going to take place? And how do you allocate the software? how do you manage parallelism, and how do you manage the memory So these are the things learned from companies. And we also saw that it's a typical case in the companies that the functionalities are typically implemented for execution on CPUs. And it's very rarely the case that we see something, a project starting from scratch. It's typically an evolution or some type of addition. So, but even in new projects, it's very common for prototypes and for experiments to be first executed on CPUs, and then you analyze the necessity of performance, and then you evaluate the feasibility of moving some portions to an accelerator. So what we saw is that there's a clear need by the companies to implement software solutions, but in a structured way, in adopting heterogeneous platforms. And we saw that this was missing. There are actually no holistic approaches to help in this migration from CPU-based software to software that can be executed on heterogeneous platforms. And for that, we developed a decision-based framework that actually includes all aspects of development process of migrating software to heterogeneous platforms, also in a systematic way. From the interviews and from the interactions, we saw that if we have something that is kind of a step-by-step process, we would successfully and efficiently address the problem and be able to guide engineers in this task. So the framework basically contains 5 stages, as you see on the screen: assessing, re-architecting, developing, deploying, and evaluating, which is kind of mimicking a traditional software engineering process, in which for each stage we have a bunch of aspects that needs to be acknowledged and a bunch of questions that need to be answered. And the framework works like this. The engineer goes over the aspects and answers the questions that we're proposing in order to come up with the decisions that are necessary to make the move. So, for instance, if you go through every stage, you will start first with assessing. The assessing, you would look into functionality analysis, you would decide what type of hardware, you would start wondering about the impact of such refactoring. You would also look into project-related issues and so forth. So here you would answer these types of questions. Is the software parallelizable in the first place? Is it even feasible to go for something like heterogeneous platforms? Then you would start the re-architecting stage, in which you determine which portions of the software are going to be executed by which type of processor. You actually determine the overall architecture design. You ask yourself which type of pattern is going to be used, or what type of architectural principles are going to be used, only to prepare for the developing stage, which is where the implementation is made. There's an adoption of the development process that is more suitable. Here is where you actually look at the components that need to be re-architected and refactored and go about doing these changes that are necessary. And then looking at deployment, these changes might need a specific deployment process in place. The hardware should also be prepared for receiving the software. So you might ask questions about the deployment policy. Is it going to be static deployment or dynamic deployment, and so forth? And the final stage is about evaluating the solution. So since we're talking about re-architecting here, it's important that we test the functionality thoroughly to make sure that the functionalities are preserved. And we also evaluate the outcomes of such refactoring to see if the performance measures they were achieved, if it was satisfactory or not. So these types of questions are answered in this last stage. There is a lot more to talk about the framework, but because the time is running up, I'm going to wrap up with the conclusions and the takeaways for this presentation. First is that there are several concerns and approaches in literature, like particular algorithms and technologies, but an overall approach is missing. So we see that there is interest in heterogeneous computing and software development for these platforms, but a holistic approach is missing. So a step-by-step process is missing. So, and we also noticed that, number two, many companies are in the starting phase of adopting, so prototyping, making experiments, trying out different technologies. And of course, some bigger ones are more mature in that, but most companies that we interviewed are in that stage. There is interest, but there are these difficulties that need to be overcome. And number three, we developed this framework to assist engineers in this process of adopting heterogeneous platforms. And we went out, we had case studies, and we handed out questionnaires, and we had positive feedback about this framework. So with this, I closed the presentation part. If there are any questions about this or any inquiries, please don't hesitate to contact me. Thank you very much.
Very good, Hugo. I will at this point stop the recording of the seminar, and then if I could only figure out how to do that, there we go.